ഹലോ കുട്ടികളെ, നമ്മൾ പുതിയ ചാപ്റ്റർ തുടങ്ങാൻ പോവാണ്. മോഡ്യൂൾ അത് തന്നെയാണ്, മോഡ്യൂൾ 3. സോ ദിസ് ചാപ്റ്റർ ഈസ് integration in vector fields. So this is chapter 14 from textbook. Chapter 14 from Thomas and Finney, integration in vector fields. So integral calculus continued. First we will start with line integrals. Line integrals. Contour integrals എന്ന് പറയും. നമ്മൾ പാരാമീറ്ററൈസ്ഡ് കർവ് എന്താണെന്നൊക്കെ പഠിച്ചിട്ടുണ്ട് കഴിഞ്ഞ സെമിസ്റ്ററിൽ. So what is a parameterized curve? Suppose we have the xyz space. X-axis, y-axis, z-axis. A parameterized curve means you can think of a particle moving in this space with respect to time. So this is the time interval. Let us say a comma b. When time t equal to a, particle was here. So this is denoted by r of a or r of t. This is r of a, vector r of a, and this point is vector r of b. So these are the position vectors of the particle at time t equal to a and time t equal to b. And at an arbitrary time t, suppose the particle reaches here, r of t. So this is the position vector of the particle at time t. So parameterized curve can be represented as, you can give a name for this, c. So c is parameterized as r of t equal to let us say x of t vector I plus y of t vector j plus z of t vector k a less than or equal to t less than or equal to b, where x of t, y of t, z of t, these are the coordinates of the particle at time t. So at time t, the particle was at a distance x of t in the x direction, y of t from the y direction, and z of t in the z direction. Okay, now suppose we have a function defined over a domain which contains this parameterized curve c. Parameterized curve c, they are also called as contours. So suppose you have this is the domain of a function f which contains this contour c, and that function f, it's a real valued function. So this is the real line and f. If x comma y comma z is a point here, then what is the value of f at this point x comma y comma z? It is f of x comma y comma z. Okay. Similarly, this is the point x of t comma y of t comma z of t, or x of t vector I plus y of t vector j plus z of t vector k. We can use any notation, whatever is convenient. So what is the value of f at this point? It is f of x of t comma y of t comma z of t. That means f of r of t. Okay, that is the value of the function at this point. Okay. Now look at the composition. So from here to here you have the function r, vector r. So start with the t, go to r of t, then take f of that, f of r of t. That means you can draw a line from here to here. So this is the composite function f of r of t. That means f of x of t comma y of t comma z of t. Okay. So this is the setup. Now I want to define a concept like integral over c, integral over this curve f, and I am integrating with respect to the arc length. Arc length, remember, it is denoted by s. And we have learned the formula for arc length s, which we will see in the next board. And I want to integrate this f with respect to this arc length. So ds is an elementary arc length, arc length of a small portion of c. And I want to define the notion of this thing. So what we do is we partition this c into smaller subarcs. First subarc, second subarc, third subarc, and so on. And in each subarc, so suppose that this is a typical subarc, kth subarc. Suppose the length of this kth subarc d, let us say delta sk. So delta sk denotes the length of the kth subarc sk. Let me write it. So let delta sk denote the length of the kth subarc sk. Okay. Now let us choose an arbitrary point xk comma yk comma zk in each subarc sk. So choose an arbitrary point xk comma yk comma zk in each subarc sk. So k running from 1 to n, let us say. That means total number of subarcs is n. Okay. Now assume f is continuous. Oh no. Before that, we want to form a Riemann sum. So evaluate f at that point xk comma yk comma zk. So this is, let us say this is the point xk comma yk comma zk in the kth subarc. This point xk yk zk. Like that you choose an arbitrary point in each subarc. Now form the sum f of xk comma yk comma zk. That means you evaluate f at that point and multiply by the length delta sk. This is small s. This is small s, not capital S, because capital S will be used for some other purpose later. Now you form the sum sigma k equal to 1 to n. What is this? Okay, running from 1 to n. So this is a Riemann sum. This is a Riemann sum. And suppose f is continuous. Continuous in its domain, and if your contour or the parameterized curve is smooth, and if C is smooth, then we can show that this sum, the above sum, approaches a finite limit. Approaches a finite limit as n tends to infinity. That means when the number of subarcs becomes increasingly high, this sum approaches a limit, and that limit is called the value of this integral over C f ds equal to limit n tends to infinity sigma k equal to 1 to n f of xk comma yk comma zk delta sk. And this continuity assumption, that is only necessary, it's not sufficient. That means you can have discontinuous functions also, for which integral over C f ds makes sense. Okay, so this is the definition. Remember, this definition doesn't help you to evaluate integral over C f ds. This is smallest, because you can have different partitions of the curve C, and you can have different sums like this. So each time you will get a different answer for this sum. The thing is that the limit is the same, and that limit is called integral of f over C, denoted by integral over C f d small s. Thank you.